First, I have to apologize the replacement of the speaker. Dr. Song is the original speaker, but our institute is under reorganization, and he had a very important role in this nowadays. So he could not attend this conference. So instead of him, I will make this presentation. And the first part, I will talk about the research about DeepRain and DeepTC, and later part, Seungkyun will introduce about his work called GlobeNet. So let me start. So firstly, I want to just mention about the introduction, how similar two areas, vision area and meteorology area. So I just mentioned about the similarities and differences, and I just give you a short introduction. Then we will introduce our work. Our work includes DeepRain, DeepTC, and GlobeNet. DeepRain and DeepTC, DeepRain is worked for the prediction of precipitation and using radar data, and DeepTC is work for trajectory prediction using numerical model data, and GlobeNet is utilizing the satellite image, and GlobeNet predict the trajectory of tropical cyclone. So, and then we conclude this talk. Okay, first part. Deep learning technology has been developed for the vision task first, such as classification and localization, or object detection, or instance segmentation. Location, as you almost of you know, classification is work about whether this is cat or dog, and location problem is about, okay, this is cat, and then where is cat? The frame in the picture. The object detection and segmentation is a similar problem where object is in the frame with rectangular box or exact region. There are similar needs in the meteorology side. We can cast those classification problem into the meteorological area, into classification or location or object detection or segmentation. We can cast many meteorological problems into those problems, and we want to know, we just want to know whether this is a tropical cyclone or not, and then where the cyclone is, and we in detail reason. So in summary, we can say that the tasks are similar in those two areas, because there are problems of, in two areas, there are problems of classification, location, localization, detection, and so on. And that's why sometimes we can apply those technique, previously introduced technique, to the directly to this meteorological task at a starting point. However, there are also different points between two areas. As you know, in meteorological side, in the most cases, weather data has multi-channel and multi-variable, including spatio-temporal scale. Furthermore, it's very precise data, which has double precision floating point. As for the underlying statistics, as you know, the normal images such as cat and dog has Gaussian distribution, but images of clouds such as satellite images has more skewed distribution. So we can say that is different point. And finally, it opens up here in a large scale. So these difficulties can be considered as the challenges to us. I just want to point out only the multivariable characteristic here, and I will show you some examples how much variable some meteorological data has. So here, this is COMS satellite images. They have 4 IR channels, so the basic IR channel and the shortwave IR channels. There are 4 different kind of IR channels they have. This is Himawari satellite images. Even they up to 16 channels. So we can say that in what meteorological data are very multivariate. And this is the WRF simulation data. The WRF data is a simulation data of atmospheric condition that can have dozens of atmospheric variables, such as wind, pressure, and temperatures. It's up to 100 variables we can have in this data. So we can say that is multivariable data, and let's assume that we have a forecast task using this WRF data, which has with deep learning technique. For more accurate result, we need to utilize as much as variables we can from the whole set. So this is not the easy task. It's challenging since the data is multivariate. I just mentioned what difficulties and challenges we can have when you deal with meteorological data and tasks as a short introduction. And from this part, we want to explain about our models for the weather task. So firstly, I want to give you some overall framework, or overall flows of the deep learning based weather prediction. The prediction of weather events with deep learning technique can be flowed like this. Well, we can have numerical data or sensor data and satellite image data, and then we build some kind of deep learning models with now popular deep learning techniques or method, and then we predict the disasters like tracks of typhoon or cyclone, or level of flood or surge. So for this work, we usually employ some distributed deep learning framework or a cluster with multiple GPUs. So I want to explain more in detail about DeepRain. Traditionally, precipitation is often predicted by weather radar data. As you know, weather radar data refers to the data represented by a radar image that is composed during the moving speed, direction, and strength of a signal transmitted by a radar transmitter into the atmosphere and received after it has collided with water vapors or the like. Previously, many studies in the Meteorological Society with numerical models have been conducted for this task. However, we proposed to solve this problem by a convolutional LSTM model. So in this study, we predict the total amount of rainfall between future 1 and 2 hours from the radar data here. So we do it by applying convolutional LSTM model to this data. In other words, we have radar data and its corresponding rainfall amount. By the way, the radar data consists of 15 time spans with 6-minute interval and 4 heights from the 0.5 kilometer to 3.5 kilometer with an interval of 1 kilometer. So first I need to elaborate the data. The data that we used is a research use data released by Chechen Meteorological Agency. It models specific area in Chechen as a grid pattern. Here you can see this. You can see the grid in this picture. They modeled 101 by 101 kilometers area. In the grid, each cell has a radar reflectivity values in dBg. Therefore, we have 101 by 101 numerical values for target site. When you plot the data, we can have an example like this. As you can see, the brighter part is a more cloudy area that have higher reflectivity. For the ground truth, the total amount of rainfall is measured at the center position, center area, that is 50 by 50 area in the center of the target site. This is the architecture of the DeepRain. We utilized the convolutional LSTM cell that is introduced 2015 by PSique. As input data, the model receives 15 items of data according to the time interval. The output value is generated by the last cell, which is the expected amount of rainfall. We employed many-to-one approach like this. Note that we don't have decode layer here because the data set has the reflectivity values. The data set has the reflectivity values and its corresponding amount of rainfall between future 1 and 2 hours. We trained the model, and consists of two kinds of LSTM cell. The first one is convolutional LSTM, and the second one is fully connected LSTM cell. So as you can see, the convolutional LSTM, two-stacked convolutional LSTM shows better learning performance than fully connected LSTM. And we tested the performance with the trained model. With two-stacked convolutional LSTM, we achieved 23% drop against the baseline. And then we have an extended experiment with the radar data. We built a sequence-to-sequence model to predict next step of images from the last 10 images. So we predicted 5 next images from the last 10 images. For this, we built a model that encoder part, that has encoder part here and decoder part. For dimension reduction of the input data, we modeled, we have 2 convolution layers here. So the original input data is 101 by 100, but after 2 convolution layers, we have 26 by 26 input dimension here. And we input the convoluted input for each encoder cell, and after the decoder step, we deconvolute the output of the decoder cells into the original size. And we built several conditioned models using vanilla RNN and vanilla fully connected LSTM and convolutional RNN, convolutional LSTM. As I said, we adjusted the input size by convolution operation here, but in this model, we just input the full size, the image into the convolutional RNN and convolutional LSTM. So as a result, we confirmed that the convolutional LSTM with smaller input by convolutional layers has the best result. But I just want to demonstrate some bad examples here because by our qualitative analysis, we have some bad examples for the prediction of next images. You can see this is the ground truth image, but our model predicted like this. Sometimes prediction images are very blurred because there are many possible reasons why some cases are blurred here. In this case, a very big size of blurred area is appeared. So we are now devising some ways to overcome these kind of problems. The alternative measure is we can measure the shape of this picture. I mean the shape of the cloud in this picture, and if we add the loss functions about the shape, and then we train the model with the additional loss function, I think we can get the better result, but I'm not sure. We are testing now. And the more challenging problem is that the case of the cloud here suddenly appeared in the decoding step, which was not in the input sequences. So in the case, the model can't train the when and how much clouds appear in the predicted step. So that's might be related with the optical flow problems. The unseen data we cannot predict the unseen data. So that's the other challenges for this part. Now I want to move to next topic called DeepTC. This is a work for trajectory prediction of cyclone with numerical model data. So actually this work will be introduced in this evening at a post session. So if you have some question or if you have more interest in here, so please come and visit and talk with me. So some of you may know that the model data, and I mean the numerical model in meteorological society, like WRF or MAP, I mean MPAS. So that numerical models simulate the conditions of the atmospheric conditions. So those model data and meteorological lists rely on those model data to predict wind speed, precipitation, air pressure, and so on. But in this work, we utilize these data to predict a cyclone path, cyclone trajectory. So our idea is that to predict the typhoon track using data from numerical model, which is simulate the actual conditions, the conditions of air or atmospheric conditions with deep neural network. We also use convolutional LSTM model here, and we utilize the ensemble-like technique. So I need to elaborate this technique first. So with different initial values, models generate different kind of atmospheric conditions. I mean, let's assume that a typhoon is now here, and with the model with different initial values, each model predict the different kind of air conditions. So like this. So if we generate multiple simulation data and utilize it to the typhoon prediction as a ensemble-like technique, so we can give some more accurate prediction for the typhoon track. So this is actually ongoing work. For this presentation, I used 10 typhoons drifting in close proximity to the Korea Peninsula, as you see here. So I said that the WRF or MPAS can be generated up to 100 dozens of atmospheric variables they can generate, but I just selected only 5 variables deemed to be the most significant for the cyclone tracking. They are all 4-dimensional. Time, which has time, height, width, and length. This is actually, length is actually the altitude. So the variables can be perturbation, potential temperature, or and perturbation press, like this. So we generated the simulation data with 10 typhoons. Totally, we have 10,060 predictions. We simulated the data every 6 hours cyclically with 5 different initial conditions. So 5 different initial models can generate 5 different air conditions. And total, we have this amount of data, and we validated training into training data set, validation data set, and test data set. So similarly, we built a convolutional 2D LSTM model here. Let's note that this is a many-to-many structure while DeepRain has many-to-one approach. We have WRF data here and its corresponding best track of the tropical cyclone with different models. And we generated the estimated longitude and longitude for each time scale. So actually this time scale is 6 hours, and we have 5 time scale time interval here, and it's actually next 24 hours. So we trained the model with the data, and the training loss reduced like this. And additionally, we tested multiple devices, CPU and 2 K40M, GPU and 2 PBAC, 2 P100 GPU. So as you can see, the twice of the performance in training you can check. And with the test data set, with the trained model, we get 13.5 in RMSE. So in this work, we are just checked how we can utilize the numerical model data into deep learning technique, like ensemble technique. So in this initial experiment, we just check the feasibility, and we are now employing more typhoons, up to 50, and we are train the model with the expanded data. So, and now we will, I will introduce Hong, Mr. Hong will talk about his work about GlobeNet.
Sure. Greetings, everybody. I'm Seongchan Hong from Korea Institute of Science and Technology Information. I'm happy to be here to share our recent researches about training and learning some typhoon track prediction using satellite images only, and autoencoder, convolutional autoencoder for understanding some movement of the clouds and some more atmospheric movements through the neural networks. So let's think about that. Previous two researches, the name of DeepRain and DeepTC, actually they are using some, actually DeepRain is using the radar images, and DeepTC use the numerical weather data models. So unlikely compared to the numerical weather models, we just thought that what if we can use some satellite images for predicting the future weather events, because actually the numerical weather models actually simulate some weather situations, but at least the satellite images actually depicts the real current situations of the weather events. So if we prepare some long-term sequence of the satellite images, and if we can successfully train some movements or some other aspect of the movement of the clouds, then we can say that we can learn something from the historical satellite images. So we can prepare some satellite images from Korean Meteorological Agency as well as the Japan Meteorological Agencies, and we can have some well-known image-based deep neural networks such as convolutional neural networks, as well as the long short-term memory for predicting some long-term time sequence prediction. And we have some track data. Track data means that the result of the movement of the typhoons. Actually, this data is from some many other weather organizations, such as the Japan Meteorological Agency like RSMC, as well as the NOAA. So here what the data we used is, we used the COMS1 satellite images. As the Kim said before, we used the 4 channels. So there are regular IR channels and shortwave IR channels, and some long wavelengths IR images. And we actually used about 5 years from April 2011 through the December 2016, and so these satellite images for using for input data, and for the label data we use the RSMC Tokyo Best Track. Actually the RSMC is the research center for predicting the upcoming typhoon tracks through the Southeast Asia, and we used also the 6 years of the data. So we used the 6 years, and also we used the same 6 years of the typhoon tracks for predicting the location, the position of the satellite image. So we cover about 152 typhoon cases. So here is some examples of the satellite images. So we have 4 satellite images, and we plot about 5 years of the typhoon tracks on some 2D metrics. So this is an actual result of the typhoon tracks, and we suggest about two convolutional neural networks. So first one is just a simple convolutional layers based CNN, and the second one is inception based model. For the first model, convolutional based model, is just use a simple 3x3 patch convolutional layers. So, and we organized about 16 depths, about 64 and 256 and 512 depths of the convolutional filters, and these layers, these convolution layers, actually connected to the flattened layer and the linear regression layers, as I will discover later. And the second model, this second model consists of two convolution layers followed by the inception unit named. Actually, the inception unit is actually borrowed from the Google's inception model. So there are some 4 different paths of the convolutional filters. So just multiply the single convolution layers, and here we use the 1x1 and 3x3 and 1x1 and 5x5, and just max pool the input image and apply one more convolutional filters with 1x1, and we can concat all of these filtered images. So we compare to the simple layer model. Actually, the simple model, output of the simple model is about 512 filters, but for the inception based model, we increase these filters into about 3072 filtered images. So, and then this filtered image is flattened for extracting the features, and then we organize about some 4 linear just dense layers to make 2 output. The 2 output is like altitude and longitude. No, not altitude, longitude and latitude. So finally, this is a result of the both models that I described before. So the best model is use the complex model, the inception based model with the activation function as a LU and hyperbolic tangent for some predicting at the linear regression. And here is our testing result. So it is said that a distance of the eye of the typhoon is about 30 to 65 kilometers, but our result is, I think we can well, here are some outliers, but we can see that our prediction is very close to the actual predictions. And we actually organized another model, the autoencoder. Actually, the autoencoder model is for making a new neural network model for understanding how the actual weather situations are presented. Or so we organized some convolutional neural network based models. So we prepared for only the COMS1 satellite images, we prepared at least 16 terabytes of the images from 2011 to 2017, and so about 180,000 scenes exist now, and we are also doing some analyzing on some Himari 8 satellite images. So basic idea of the convolutional autoencoder of the GlobeNet is we extract some visible features at the encoder step, and we have a latent vector, and we decoding the latent information to regenerate the satellite images. So here are some examples of the convolution steps. For this network, we organize about 5 layers of the convolutional encoder. So this is the input data, and as the layers goes by, then we extract some visible features. And because we use these convolutional layers for striding, we use actually striding for reducing the size of the image. So the filtered image is actually decreased by 2. And here is the decoding step of the images. At the decoding step, actually we regenerate the images from the latent information. So also we passed about 5 layers, then we can generate the satellite images looks like. And at the moment when we use this autoencoder layer, autoencoder model last year, we are on a lack of the satellite. We are lack of the data set, so we use some trick to make some more elaborate, for more precise prediction. So here is our usual convolutional encoding and decoding model for generating the satellite images. But at the moment last year, we used a skip connection to the autoencoder. Skip connection is a trick to borrow information at the convolutional step, and we can use some information at the decoding step. So we can borrow some filtered images at here, and then we can pass through the decoding step. So this is our last result of the last year's research. So here is our input image, and after the decoding step with the skip connection, we can generate similar images compared to the input layers. And at this year, we are trying to generate a decoding image without using the skip connection. So this is using the skip connection, and this is without skip connection. But this year we have about 180,000 images. So I believe that we can generate we can put more of effort to generate some realistic images. And on application of this skip connection convolutional autoencoder is named PSique. Actually, this research was discussed at last year's NIPS 2017 workshop, and we try to predict our future weather images using this convolutional autoencoder as well as the convolutional LSTM for generating and learning some the changes through time. So we have our encoder part and decoder part borrowed from the convolutional autoencoder, and we organized both sequence to sequence using the convolutional LSTM cell. So encoder part of the LSTM, we gathered about 4 time steps of previous images, and then we extract the output as well as the hidden state from the encoder, and we extract the latent information from the encoder to the decoder and generate the image. And also we borrowed the skip connection structure from previous research, and actually this model is discussed at this year's GTC 2018. So actually we try to boost how can we boost this model training speed in many environments. So if you have a question, then you can visit my poster session. And so here is the conclusion. So deep learning technologies can be applied effectively to understand some meteorological phenomenon. So DeepRain does some predicting the precipitation ratio using the radar reflectivity data, and DeepTC trains trained and used for predicting the tracks of the typhoon using the numerical weather model data, and GlobeNet predicts some meteorological phenomenon. Both of the phenomenons. First one is finding the location of the typhoon, as well as learning some hidden information from the satellite images. So here is a technical issues that we need a very heavy computational resource to do this model. So we need some distributed deep learning platform, as well as we have many undiscovered some associated changes also exist. So we need to do better, and we are actually open to do collaboration with our institute, so we can have some more chance to do those researches with us. So this is end of our presentations.